Hi guys, it's Mrs. Milson. We're going to do the check your understanding on page 752 to 753, which is inference for linear regression or inference for slope. Okay. Does fidgeting keep you slim? Some people don't gain weight even when they overeat. Perhaps fidgeting and other non-exercise activity, NEA, explain why some people may spontaneously increase non-exercise activity when fed more. Researchers deliberately overfed a random sample of 16 healthy young adults for 8 weeks. They measured fat gain in kilograms as the response variable and the change in energy use in calories from activity other than deliberate exercise, like fidgeting, daily living, and the like, as the explanatory variable. So here's our data. We've got a whole bunch of computer outputs. We have a scatter plot with a least squared regression line superimposed on it. We have a residual plot. Remember, the residuals are the difference between the observed and the predicted values, okay? A good scatter on our residual. And then we have a histogram of our residuals, and I'll talk about that in a second. And we have this whole printout so that we can find the correlation, we can find the coefficient of determination, we can find the standard deviation of our residuals, we can write the linear regression equation. But now we've got some more stuff we're going to use. Okay, so we're going to construct and interpret a 95% confidence interval for the slope of the true population regression line. Okay, so again, for a confidence interval, the first thing we have to do is our state. What is it that we are trying to predict, or trying to estimate, rather? We're trying to estimate that slope for the true population regression line. But we have to put some context into it. So we will estimate B or beta, the true population slope of the regression line relating fat gain to change in NEA, that non-exercise activity, with a 95% confidence level. Okay, we're going to go through our plan just like we would before, but there's a few extra conditions for slope. Okay, first of all, what kind of inference is this? This is a T interval, because we're going to use a critical T for slope. The calculator has it as lin-reg T interval, okay? We probably won't have to run it in the calculator though, but just so you can recognize it in the calculator. Our conditions, the first three are exactly what you would think the first three would be, okay? Random. It did state that there was a random sample of young adults, 16 young adults. Our independent says, our 10% rule says, I'm pretty sure there's more than 160 young adults, and indeed young adults are independent. And then back to normal, okay? Now, how do I determine normal? It's not like I have n times p or central limit theorem here. So what are the ways that I determine normality with linear regression? Most of the time we use the normal probability plot if we had it, okay? We don't have that for us in front of us, so we can't use that. So what we're going to do is look at the residuals. Now when we graph the residuals in a histogram, they look fairly symmetrical, and there's no major outliers. So we can use that. I'm going to say residuals histogram. Let me put that in there. The histogram of the residuals histogram, is fairly symmetrical and has no outliers. Okay. And again, if we had a normal probability plot, if you recall, a normal probability plot, if it looks linear, then that means the distribution is normal, okay, or the residuals are normal. The two other conditions, the next one is quite obvious, I think, since it is linear regression. Linear regression is the data linear, okay? So the two things we look at to prove linearity is, of course, the scatter plot, how strong is the association, and the residual plot, how scattered are the residuals, okay? Well, the scatter plot, fairly, somewhat strong negative linear association, and the residuals are very scattered, no discernible pattern. So between those two, we can prove the linear conditions. Scatter plot has somewhat strong negative linear association, and the residual plot is scattered with no discernible pattern. The other condition we're going to look at with our residual plot is how evenly distributed are these residuals. Do I have the same amount above the zero line, the same amount below? So 1, 2, 3, 4, 5, 6, 7 above, 1, 2, 3, 4, 5, 6, 7, 8, 9 below. Fairly evenly distributed, okay? So I say the condition is called equal SD. So think about kind of the spread of the residuals. SD doesn't really make sense, but anyway. So the residuals are equally distributed above and below the 0 line in our residual plot, okay? So those, we've got a lot more conditions. We have the first three. We got to talk about the scatter plot and the residual plot to prove linearity or to satisfy linearity condition, and then we'll talk about how the residuals are, you know, kind of evenly distributed about that 0 line in the residual plot, okay? Now we're ready to do the do. Let me come back up here. Now, if you will recall, confidence intervals are our point estimate plus or minus, let me write that down, our point estimate plus or minus our critical value times the standard error. Okay, well, for slope, our point estimate is our sample slope. Okay, so there's our sample slope. So that's going to be our point estimate. So negative 0.00344415 plus or minus. I am going to use a critical T. So I'll do the critical T here as an aside. Well, first of all, how do we do our critical T? Can't really remember. Critical T, remember, it kind of acts like a critical Z. If we have the middle 95%, because that's the confidence level we're going to do, I've got 2.5% on each tail. So my critical value here is the critical T for the 97.5. So we have to go into, let me move that, looking a little funny with the light. Okay, I think that looks okay. My second vars, okay, and I go to my inverse T, if we've kind of forgotten how to do that. I put in my area, of course to the left is 0.975, and now what's my degree of freedom? For linear regression, your degree of freedom is now n minus 2. Why minus 2? Because you've got two variables you're working with. So degree of freedom is n minus 2, and if you'll recall, there were 16 young adults used in the sample. So 16 minus 2 is 14. My degree of freedom is 14, so I'll put that in. So my critical T is 2.145. I'll use that, okay? So 2.145 is my critical T. And then I have to do the standard error, okay? Standard error is usually the standard deviation of the sampling distribution, but we don't really have that like we did in means and proportions, but that's okay because it's on my printout, okay? It's the second one. It's the second one in the line here, okay? Don't worry about that one. Don't worry about any of this top line. There's my standard error, okay? So I'll multiply that by, okay? So there's really not a lot you're going to be putting in the calculator per se. Everything you're going to get for your actual do section of your interval is going to be from your printout, okay? So of course, I'm going to throw that part in the calculator because again, remember that part is my margin of error. Okay, so I'll put that in the calculator, and I got plus or minus, and put it in your calculator. Make sure you agree with me. So there's my margin of error. So of course, to get my interval, I'm going to subtract and I'm going to add, and then I get my interval to that. Okay, so you can tell my interval goes from negative to negative. So that means there definitely is a negative slope, okay? My conclusion is pretty much exactly the same. I'm 95% confident that the interval negative 0.00503 to negative 0.00185 captures the true population slope of the regression line relating fat gain to change in NEA. So I will put that up there for you to read. Okay, and again, since the interval is negative to negative, then there truly is a we do have evidence that there is a negative slope. There is a negative association between those two variables. Okay, great. I'll see you next time.